Unit 6, pages 188 to 191. Applying the fundamental theorem of calculus, which we'll also call FTOC for short. You can call it FTOC. Connecting the graphical, analytical, and numerical approaches. So the fundamental theorem of calculus, part 1, there's the part 2, states that if little f of x is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then the definite interval from a to b of little f of x dx is equal to capital F of b minus capital F of a, where capital F of x is the antiderivative of little f of x. It's a mouthful. However, we are going to do a couple examples to explain what it is actually stating. So we're going to consider the function f of x equaling negative 2x plus 3, whose graph is pictured below. We're going to use the same equation and same graph for the next 5 examples. We want to calculate each of the following definite integrals according to the fundamental theorem of calculus. Then we want to shade the area of the region that the integral represents. So we're first going to figure out what the answer to this definite integral is using FTOC. So our first step in using FTOC is we first need to figure out what the antiderivative of the function is. So in this case, our antiderivative, right, we want to add 1 to all the x values, and then we want to divide our coefficient by our new exponents. So we have negative 2 over 2 and 3 over 1, and then we add our c. Since we're looking at definite integrals, we want to make sure that we keep in mind what the interval is that we're trying to find. Then we can simplify. We have negative x squared plus 3x on the interval from negative 2 to 1. So using FTOC, we know that f of b minus f of a is what we're looking for. Right? If our b is 1 and our a is 2, that means that we're looking at negative 1 squared plus 3 times 1 plus c minus negative 2 squared plus 3 times negative 2 plus c, which will give us negative 1 plus 3 plus c minus negative 4 minus 6 plus c. When we distribute that negative sign, we'll get negative 1 plus 3 plus c plus 4 plus 6 minus c. The c's will cancel out, and that's the case for any time you're using FTOC with a definite integral. Right, so then we'll get our final answer, which is 12. So now we want to make sure that when we find the shaded region on the graph, it also equals 12. So since we're looking at the interval from negative 2 to 1, that means that we're looking at the space between the curve of the graph and the x-axis. And in our case, that creates a trapezoid. The area of a trapezoid is equal to 1/2 times the height times base 1 plus base 2. So we'll have area equals 1/2. Our height is 3. Our first base is 1, 2, 3, 4, 5, 6, 7. And our second base is 1. 7 plus 1. So our area is 12, which matches what we found analytically. Okay. So we're going to do another problem, not the one right underneath, but I do want to state that since we're using the same equation, we do know what the antiderivative is for each of these equations since we found it in the first problem. And since we're using photoc, we don't actually need the plus c. So when you're finding the antiderivative of this next problem, you don't need to put the plus c. It's just going to be negative x squared plus 3x, and we're looking on the interval from 2 to 5. Okay, so I want you to work on that problem on your own, analytically and graphically, just to make sure that your answers are going to be the same. Okay, now we're going to move on to problem number 3. Again, same function, so the antiderivative is negative x squared plus 3x, but now our interval is from negative 1 to 4. So again, using photoc, f of b minus f of a, we'll have negative 4 squared plus 3 times 4 minus negative 1 squared plus 3 times negative 1. No need for the c. So that gives us negative 16 plus 12 plus 1 plus 3, which is equal to 0. Interesting. So if we look graphically at how we could possibly equal 0, if we're looking at area under the curve. So we're starting at negative 1 and we're going to 4. Just a reminder that when you're looking at an integral, you're looking for the area between the curve and the x-axis, right? So we're looking at the area between the curve and the x-axis. So here, that area will be positive. And here, since that part of the graph is below the x-axis, that area will be negative. And we seem to have two triangles here, so our area of a triangle is 1/2 base times height. So we have area of our first triangle, which is 1/2. Our base is about 2.5, and our height is 5. And we're going to add to that 1/2, a base of 2.5, and a height of, in this case, negative 5, since we're below the x-axis. So my area is 6.25 minus 6.25, which is equal to 0. Right? We're going to do one more problem on this page just to get in the habit of identifying when an area will be negative. So here, again, our antiderivative is negative x squared plus 3x, and we're looking at the interval from negative 1 to 3. So photoc says f of b minus f of a. My b is 3, so we have negative 3 squared plus 3 times 3 minus negative 1 squared plus 3 times negative 1. So we'll get negative 9 plus 9 plus 1 plus 3, which is equal to 4. So graphically, we're looking from negative 1 to 3, and we're looking at the area between the curve and the x-axis. So we're above the x-axis, and then we're below the x-axis. So this area will be positive, this area will be negative. So again, we're looking at two triangles. So the area of my first triangle is 1/2, a base of 2.5, and a height of 5, plus 1/2, a base of 1.5, and a height of negative 3. So we have area equals 6.25 plus negative 2.25, which is equal to 4. Right? So try that last problem on this page on your own, remembering that if the area is below the x-axis, then we're looking at a negative value. So based on the results of the 5 previous examples, we can make a few inferences about the value of definite integrals and the amount of area bounded by the graph of the integrand and the x-axis. First inference that we can make is that if f of the integral from a to b of f of x dx equals the area of the region bounded by f of x, the function, and the x-axis, right? It's the area between the curve and the x-axis, not just the area under the curve. Second thing we can state is that if the definite integral from a to b of f of x dx is greater than 0, then the region bounded by f of x and the x-axis is larger above the x-axis than it is below. Right, so there's more area above the x-axis than there is below the x-axis on that interval. Right, so on the interval from a to b. If the definite integral from a to b of f of x dx is less than 0, the region bounded by f of x and the x-axis is larger below the x-axis than it is above on the interval from a to b. And the fourth statement that we can make is if the definite integral from a to b of f of x dx is equal to 0, then the regions above and below the x-axis are congruent. Okay, so it doesn't mean they look the same, it just means that they have the same area, they have the same space. So what we're going to do now is we're going to apply the fundamental theorem of calculus to the definite integrals below, and we can use our graphing calculator to verify our results, and I'll show you how to do that tomorrow in class. Okay, so I'm not going to do all of these problems, I'm only going to do one, and that'll be the first one. So first thing we want to do is find the antiderivative. So we're going to add 1 to all the exponents, and then we're going to divide our coefficient by our new exponent. And since we're finding definite integrals, we don't need the plus c. We just need to identify our intervals. We can simplify this to x squared minus 1/3 x cubed from -1 to 2. So Fatak tells us find f of b, subtract from it f of a. So we'll have 2 squared minus 1/3 2 cubed minus -1 squared minus 1/3 negative cubed, which will give us 4 minus 8/3 minus 1 minus 1/3. Which is equal to 4 minus 1 minus 3, because -8/3 minus 1/3 is equal to -9/3, which reduces to -3. And this equals 0, which tells us that the area, the region above the x-axis and the region below the x-axis are congruent on this interval. Okay, so try the next two problems. I'll show you how to verify using the calculator in class tomorrow. So pictured below is a table of values that shows the values of a function f of x and its first and second derivative for selected values of x. We want to use this information in the table to answer the questions that follow. First question is, what is the value of the definite integral from -3 to 1 of f prime of x dx? First thing we want to do is identify what the antiderivative of this is. The antiderivative of f prime of x is f of x. So we want to find f of x from the interval from -3 to 1. So Fatak tells us we need f of b minus f of a. So that'll be f of 1 minus f of -3, which is equal to -2 minus 4, which is -6. Okay. Similarly, 2 and 3 do not require too much work, because when you find the antiderivative of 2, that is just saying the antiderivative of f prime of x is f of x, and the antiderivative of f double prime of x is f prime of x. And we're looking for the interval from -1 to 3. So we'll need f of 3 plus f prime of 3 minus f of -1 plus f prime of -1, which is equal to 1 plus 3 minus 0 minus 1, which is equal to 3. Try number 3 on your own, remembering that the coefficient isn't going to go anywhere. You can pull it right out of the integrand sign if you would like. Similarly with number 4, the coefficient won't bother you. Just pull it right out of the integral sign and just integrate the f prime and the f double prime. Okay. So now we want to write the equation of the tangent line to the graph of f of x at x equals 3. There isn't much we need to know here except for the point of the tangency and the slope of the tangency. Point of the tangency we find by plugging in 3 into our original function. So f of 3 is equal to 1, so our point is 3, 1. And slope of tangency we find by plugging in 3 into our first derivative. So our slope of tangency is 3. So our final equation is y minus 1 equals 3 times x minus 3. Just a little bit of review from previous units. So now use that equation to approximate the value f of 3.1. We want to know if it's an over approximation or an under approximation. And I'm going to help you out with that by giving you some information. You want to know, are we concave up or concave down at x equals 3? Right, that will help you determine if we're going to be an over approximation or an under approximation.